but I'm going to have to go and knock some off. Okay, welcome back everyone to Math 131. We're at Lecture 6. We were pushing it yesterday to get into that limit definition of the derivative. We're definitely coming back here, but first I wanted us to just do a little bit of warm-up and some cleanup of limits, evaluating limits if they exist. And of course then we're going back into the limit definition of the derivative, which is on page 87. We're going to move into continuity and differentiability, and this is really what does it mean when a function is continuous at a point or differentiable at a point. And I forgot to write down higher order derivatives. And I think that's section 1.6. Is that section 1.6? No, that's the rules. We've already done the rules. Higher order derivatives, 1.7. I'll probably slide that in early on us. That's pretty straightforward. It's just what is it? We're going to be using not only the first derivative, but we will also be using what's called a second derivative when we start our curve sketching by using derivatives, which the reason for that is to lead into the applications so we know how to identify maximum and minimum values of functions. Okay, so that we'll go only through the second derivative, although your book probably has you do a couple third derivatives and stuff. I don't think in this course, well, I know in this course you want, or the next course you take, but if you were in engineering calculus, you'd do things like Taylor series and Taylor polynomials, and you get into higher order derivatives. So there really are applications for going to a second, a third, and a fourth, and a fifth, but I don't believe you'll get it in your one. I know you won't get it in 131, and I don't think 231. All right, so we will get started. Tomorrow will be definitely the review day because the test is the next day after that. Okay, we want to warm up a little bit with limits, and the idea is what does it mean, and let's visualize what the answer is. First example, we want to look at the limit as x heads off to infinity of 1 over x. All right, remember the 1 over x is like your y value, y equals. And this says as I keep putting in bigger and bigger values for x, what does the y value, 1 over x, get closer and closer to?
0.
0. So you start thinking of numbers like 1 over 100, 1 over 1,000, 1 over a million. And if you relate that to food, 1/100th of a pie is not very much, or a candy bar. 1,000th of a piece is definitely not very much. This approaches 0. Very good. All right. What about if I have the limit as x approaches 0 of 1 over x? I'm getting close. Okay, I'm getting very close to 0 on both sides. X is approaching 0 from around it. Okay, what's a number real close to 0? Okay, so a number might be 0.0001. All right, well that's tenths, hundredths, thousandths, 10 thousandths. That's 1 over 10,000. So if I put 1 divided by 1 over 10,000, what is that number?
10,000.
10,000, right? So if I even did even closer to 0, oops, did I put enough in there? That's tenths, hundredths, thousandths, 10 thousandths, hundredths, thousandths. 1 divided by 1 over 100,000. When you flip that over, that gives you positive 100,000. So if you're real close to 0, you're looking at the limit as x approaches 0 on the right. That's where I just did that, of 1 over x. Where are these values going? What are the y values getting closer and closer to? Infinity, right? Because 1 over 1,000 is 1,000. 1 over 10,000 is 10,000. So this is headed in the direction of positive infinity. Let's go on the left side. A number on the left side would be like negative 0.0001, which is negative 1 over 10 hundredths, thousands, 10 thousandths. negative 1 over 10,000. So if you have 1 divided by negative 1 over 10,000 is going to be negative 10,000. So what is happening to 1 over x as x gets real close to it from the left? It's going to negative infinity. So what is your answer on a test going to be when you have the limit as x goes to 0 of 1 over x? Does not exist. Because when you came in from both sides of 0, one went up, one went down. Let's take a quick visual of this. What's the graph of 1 over x look like anyway? Hyperbolas, yeah. Looks like this and like this. Okay? So the first question said as x went to infinity, x got bigger and bigger and bigger. You see that y value getting closer and closer to the x-axis, which is y equal to 0. Do I have an asymptote here? Asymptote. Yeah, what is it?
X-axis.
The x-axis. What's the equation for the x-axis?
Y is equal to 0.
Y equals 0. Okay. Then as x gets closer and closer to 0, you came in this direction and you came in this direction. By picking points real close to 0, we knew from the right it was going to head in the direction of positive infinity. From the left, it was going in the direction of negative infinity. So we had to say it didn't approach the same direction or number, so the limit does not exist. Do we have another asymptote here? The y-axis, and that is x equals 0. Remember, a horizontal asymptote is as x gets really, really big or really, really small, the curve approaches that. A vertical asymptote is that as you get real close to it, your curve is going to fly off to positive infinity or down to negative infinity. Okay? All right. One question like your webassign, because somebody asked me. Limit as x approaches infinity of something like 2x plus 1 over 5x minus 3. All right, let's remember that we have, our function is y equals 2x plus 1 over 5x minus 3. And this does not simplify, Okay, from your pre-calculus days, what is the graph of this going to be? Hyperbola, correct. Okay, where is this undefined? At x equal to 3/5. So you know you're going to have a vertical asymptote at x equal to 3/5 because that's what makes the denominator equal to 0, right? What is your horizontal asymptote? You memorized a theorem in your pre-calculus class. What's your horizontal asymptote?
Y is equal to 2 over 5.
Right. Y is equal to 2/5. Y is equal to 2/5. You look for the term of highest power in the numerator and the term of highest power in the denominator, and if they're the same, you just use the coefficients. That, which is 2/5. That's a shortcut of long division. You could do long division, 5x minus 3 into 2x plus 1, and you'd find that it's 2/5 plus some little fraction. So as x gets really, really big, another way to think about this, as x gets really, really big, a 1 and a negative 3 in the numerator and denominator is pitiful, right? If you're really big, if x is 1,000,000, if you had 2,000,000, you probably wouldn't care about having somebody give you another $1, right? Or if you had 1,000,000 and you put it in the denominator, you'd have 5,000,000. You probably wouldn't get too upset about sharing $3 with somebody else. The 1 and the 3, as x gets really big, are just pitiful little numbers. So what happens is, as x gets really, really big, this function takes on y equals 2x over 5x, which reduces to 2/5. So the line y equal to 2/5 is your horizontal asymptote. So now the question is, as x gets really, really big, pitiful 1 and negative 3, this function starts to look like 2x over 5x, and so the answer is 2/5. Okay, so and that is your horizontal asymptote. Okay, let's try one more. Y'all are having kind of a blank look. All right. As x gets really, really big, which of these terms in the numerator is most important? Minus 7x squared. As x gets really, really big, which term in the denominator is most important? 2x squared. So we're just going to break this down to the limit as x approaches infinity of minus 7x squared over 2x squared. Does that simplify further? To minus 7/2. So the limit as x goes to infinity is minus 7/2. Okay, so if you were going to graph this curve, you would have a horizontal asymptote at negative 7/2, and the curve would start to approach it.
What if the numerator and denominator had different degrees?
You are so good. Let's try that. Thank you for that question. All right, what about this one? The limit as x approaches infinity of 3x squared plus 1 over 5x to the 4th minus 2. All right, let's think what's really important as x goes to infinity. 3x squared over 5x to the 4th. And we'll simplify that. Limit as x goes to infinity, and we have a 3 over a 5x squared, right? Mm-hmm. Okay, as x gets really, really big, you're looking at 3 over 5 million, 3 over 5 billion, 3 over 5 trillion. That's as far as I know. Because zillion's not really a word. Okay, so where's this thing happening when you got a little number over a huge number? Where's it going?
0.
0, right? You could think of this as 3 times 1 over 5x squared. Is that easier to see? As x goes to infinity, 1 over 5x squared. 1 over a huge number is going to 0. 0 times 3 is 0. Okay? Try one more. Limit as x goes to infinity of 4x cubed plus 1 over x minus 2. Tell me what that is. What do you think? Give me an answer. Infinity. The limit's not going to exist. Now, these examples where we're looking at the dominating term, these were when x was headed out to infinity. It was not x going to 3 or x going to 0. Because if you tried to put in infinity, you basically got an infinity over an infinity. And that's called an indeterminate form, just like when we got that 0 over 0, we simplified. Infinity over infinity is another indeterminate form. So this is almost the limit as x goes to infinity of 4x cubed over x, which is almost the limit only because we're headed to infinity of 4x squared, and that's just going out of sight to infinity. Okay? Is that good? All righty. I did this the other day, but actually this is chapter 1, section 7. Just want to kind of clean this up again, and then we'll be back into limit definition of the derivative. This is pretty much notation, higher order derivatives. Okay, let's just start with y equals x to the 4th. And we might call it f of x. How do we represent the derivative, the notation? f prime of x, what's another way? dy dx, what's another way? The derivative of x to the fourth over dx. Remember the y, you put in exactly what the y is. All right. So the derivative of x is what? 4x cubed. I know that sounds too easy, but I'm trying to get into higher order derivatives. Okay? All right. Suppose I wanted to take the derivative of the derivative. That's called second derivative. The derivative of the derivative. So if it's f prime, I just do f double prime. That means I'm taking the derivative of the derivative. Now the notation in terms of dy dx is a little strange looking, I think. But I'm taking the second derivative of y with respect to x. Actually, you don't usually use parentheses there. It's usually d squared y dx squared. I don't know why they did it that way, but that's the way it is. D squared y over dx squared says I'm taking the second derivative of y with respect to x, and that's just the notation for second derivative. Or you could write d squared and put in what your y is, which is x to the fourth over dx squared. All right, that just means you're taking the derivative of the derivative, and what is that, everybody?
12x squared.
12x squared. Okay, now in your book you'll see problems like this. S of p equals, I don't know, something like p to the fourth plus 3p plus 1. And it'll ask you to find this. The second derivative of s. I'm sorry, I always put parentheses there. Maybe we do put parentheses. I don't know why I do parentheses. Second derivative of s with respect to p, because p is my variable. And what would you tell me this is going to be?
4.
Okay, first we have to find the first derivative, right? The first derivative is 4p cubed plus 3. And now we're going to take the derivative of the derivative, and that would be 12p squared. Okay, now this is the part I wanted to slide in on you. Now they'll put this line right here and say p equal to 3. All right, what this means is I'm going to take the second derivative of s with respect to p. Left my little square off there. Second derivative of s with respect to p. Don't forget your little square I left off. I'm going to find it, and then I'm going to evaluate at p equal to 3. Okay? I'm going to evaluate at p equal to 3. This little line means evaluate. Evaluate at p equal to 3. Which would be the same thing over here if you're using this notation, s double prime at 3. Okay? Same notation. I mean, different notation meaning the same thing. All right, so we found our second derivative, and now we're ready to evaluate at p equal to 3. So we have 12 times 3 squared. 3 squared is 9. 9 times 12 is probably about 108, isn't it? 108. Okay? Remember, when you're evaluating a derivative, you got to find the derivative first, and then you plug your number in. All right, that's not too tough, is it? Good. We'll start out with something a little easy. All right. That was actually from section 1.7, but we're now headed back to the limit definition of the derivative. We're going to work some problems from the book also. Okay. This is from page 87. Limit definition. Are you expecting one of these on your test?
Sure.
Absolutely. Limit definition of the derivative. When you're taking your test, you can always and will always want to just use the rules for derivatives, except the one question, which will say, use the limit definition of the derivative. Okay? Other than that, you're using your rules. All right, so the derivative is, don't look down. I mean, don't look up. down. Don't look down. Look up and tell me what it is. I'm sorry. What is the limit definition of the derivative? Limit as h approaches 0, f of x plus h. Okay, and just to remind us where this is coming from, again, because a lot of times if you can remember what it is, where it's coming from, then it's easier to memorize. What's this little part right here without the limit? What was that? The difference quotient, which was difference between two y values over difference between two x values. And what happened was you started with your x and you went over a distance of h to get to your next x value. So that's the difference in y's over the difference in x's simplified. And that gave me the slope of what kind of line? Secant line. Secant line is through any 2 points on the curve. When you then make those 2 points almost collapse on each other, then we're looking at really a slope of a curve or slope of a, what kind of line? Tangent line to the curve. So the derivative is slope of the tangent line to the curve, which really becomes the slope of the curve at a point. All right, so I am on page 102. No, yeah, 102. And we're first going to look at problem number 44. This is page 102, number 44. I try to refer to the book a lot so you know that I really am following a book. Okay, this is page 102, so you'll see where we're coming from, right here. And we're going to use the limit definition of the derivative to find the derivative, number 44. Okay. This happens to be a fraction, so we're going to have to recall some of our good old algebra skills to solve this. F of x equals x over x plus 2. Okay? All right, so I think I better start a new page. Let's take some space. All right, so f of x is equal to x over x plus 2. All right, when you look back at your limit definition of the derivative, what else am I going to need to find before I start substituting in? Yes, f of x plus h. Remember that f of any element of the domain will be that element divided by that element plus 2. Just like if you were doing f of 5, you'd put a 5 in for x. F of t, you'd put a t in for x. So f of x plus h, what do you do?
X plus h.
For x. So x plus h, and this x gets a replacement of x plus h plus 2. Sometimes it's easier to just write it with some open parentheses and then just go put it in. All right, everybody got that? All right, so let's start with our derivative. We're using, what's this called?
The limit
Definition of the derivative. Okay, limit as h approaches 0, f of x plus h minus f of x over h. So we have the limit as h goes to 0. All right, in the place of f of x plus h, we're going to put what it is, which is x plus h over x plus h plus 2. Be very careful with that minus sign. Minus. And now we just go back up here and find out what f of x is, which is x over x plus 2 divided by h. Okay, what happens if you plug and chug h equal to 0 in here? Remember limits, first thing you do is try plugging and chugging. What do you get? You get a 0 over, you actually get 0 in the numerator. You get x over x plus 2 minus x over x plus 2. You get 0 over 0, which is called what form? Indeterminate. We need to find a way to simplify the expression. All right, this is a good old compound fraction. Compound fraction. All right, and everybody has their own little way of doing this. How do you guys like to do it? Okay, you want to get this to a single fraction and then invert and multiply? Is that what you guys like to do? Okay, so let's start in the numerator. We have the limit as h goes to 0. So up in the numerator, what is my common denominator?
H plus 8 plus 2 times H plus 2.
Right. X plus h plus 2 is its own little number like 7. X plus 2 is its own little number like 5. So your common denominator would be both of those multiplied together. All right, so our common denominator up here is x plus h plus 2 times x plus 2. All right, so the first x plus h has to be multiplied times what? X plus 2. So we'll have x plus 2 times x plus h. And then the minus x has to be multiplied times what? X plus h plus 2. Okay, so be careful with your negative sign. This is where everybody who makes a mistake usually makes a mistake. So we have times x plus h plus 2. All right, now let's clean up that numerator. So we have the limit as h goes to 0. Here's the big h in the denominator. And here's the x plus h plus 2 times x plus 2. All right, so we're going to multiply x plus 2 times x plus h, and that will give me x squared plus xh plus 2x plus 2h. All right, don't let me make a mistake. So far I'm not doing good today, am I? xh, 2x, 2h. All right. And I would encourage you to continue using parentheses till you get all this multiplied out so you don't lose your negative sign. Okay. Keep extending this. All right, now I'm going to distribute my x, so that will be x squared plus xh plus 2x. Whew. I know you can't see that on camera, can you? Not good. All right, x squared plus xh plus 2x. All right. That's better. All right. Now we want to be careful to distribute our negative and see what's going to cancel out for us. Whoops. Distribute our negative. Again, this is where mistakes are made, so you don't want to just get sloppy in your work. All right, x squared minus x squared. That's our old happy day, right? What else is going to cancel out? The xh and the minus xh and the 2x's. Good. All right, so that leaves us with the limit as h approaches 0. In the numerator, it looks like I have a 2h over x plus h plus 2 times the x plus 2 divided by h. Is that true, everybody? All right, so now we have a fraction divided by a fraction, so we're going to invert and multiply. A fraction divided by a fraction, right? So we have limit as h goes to 0, 2h over x plus h plus 2 times x plus 2. And now this h over 1, we're going to flip it over and multiply times 1 over h. A numerator divided by a denominator. Okay, and what are you happy about at this point? The h's are going to cancel out. The h's are going to cancel out for me. All right, so in the numerator we have 2. All right, so we're having a limit to evaluate. Fortunately, the h is divided out. Now let's try just plugging and chugging h equal to 0 in the denominator and see what happens. Okay, so now we're going to take the limit. In the numerator, I have a 2. What am I going to get in the denominator?
0.
The h will go to 0, so I have a x plus 2 times a x plus 2. So it's x plus 2 squared. All right, and that is the derivative of this function x over x plus 2. All right, so we have 2 over x plus 2 squared. All right, let's just talk through it quickly through the from the top, and then we'll work one more problem. All right, we had the function f of x equals x over x plus 2. We needed to know f of x plus h, so where there was an x in the original function, we replace it with x plus h. Carefully put it in there. I had a good old compound fraction. I had to simplify. We found our common denominator. We carefully distributed our negative. We ended up with a fraction divided by h. So in algebra, when you have a fraction divided by something, it's a compound fraction, so we invert and multiply. Because h is approaching 0, those factors of h can cancel out. And then when I just do my little plug and chug, that h right there went to 0, so I was left with the x plus 2 times the x plus 2. Okay? Good, everybody? All right. Let's look at problem number 34. Okay, and I'll bring the book back so we can see it. Problem number 34 was still on page 102. Problem number 34. Okay, this time it's asking us to find the derivative at 4 when f of x is the square root of 2x minus 1. All right, before it just asked us, or in the last example we just did, it just said find the derivative, okay, using limits. This one says use limits to compute the derivative at 4. So really, this particular problem does not care that we find f prime of x first, because it wants to find f prime of 4. You can find f prime of x first, but since we're using the limit definition, we can go right in with what our x is and go for it. All right, so let me write down and tell you what I'm talking about. All right, so this is page 102, number 34. We're supposed to find the derivative at 4 using limit definition, where f of x is equal to the square root of 2x minus 1. All right, remember our limit definition is the limit as h approaches 0, f of x plus h minus f of x over h. Now, when we are, if we were just using our rules here, we would have to find the derivative at x first and then substitute back. But if you're actually using the limit definition of the derivative, you can get away with putting in the 4 immediately. So you don't have to, but this is just a little bit shorter way of doing it since you're using the limit definition. We can put the 4 in because the 4 corresponds to the x. And I'll have the limit as h goes to 0, f of 4 plus h minus f of 4 over h. All right? Now let me say this again. If you were using the rules, you couldn't go put a 4 in here because you're looking for the derivative at 4. You would have to, if you were using rules, use your general power rule to find your derivative first, then put your 4 in. Everybody got that? All right. So since it only asks us to find the derivative at 4, let's just do it. All right. F of 4 is the square root of 8 minus 1, square root of 7. F of 4 plus h is going to be the square root of 2 times 4 plus h minus 1. We should have made that a plus 1. The problem would have been a lot easier to work, wouldn't it? 8 plus 1 is 9. That would have been a lot easier. Well, we like the challenge. Okay, so we can do this. So this would be the square root of 8 plus 2h minus 1, which will be 7 plus 2h, right? 7 plus 2h. All right, here we go. Limit as h goes to 0, square root of 7 plus 2h minus f of 4, square root of 7 over h. Everybody good so far? Everybody knows where the 2h came from, correct? 2 times 4 is 8. 8 minus 1 was 7 times 2h. All right, so we're ready to take a limit. You plug and chug, what happens? 0 over 0, right? If you put a 0 in for h, you're going to get 0 over 0. So we got to find a way to change the appearance of this, keep it equivalent, but change its appearance so that I can evaluate the limit. All right. First time I ever saw this, somebody had to tell me what to do, but you guys are smarter than me. So what might you do here to change the appearance? Make an exponent? That would change the way it looked, but that's not going to help me. Okay? I'd write that down except that I'm running out of space. That did change the appearance. Something else.
Could you multiply both the denominator and numerator by the top, basically, equaling 1 except for positive?
Okay, and what's that called? The conjugate? Multiplying by its conjugate? All right. Basically what she's going to do is say, well, those square roots in there, let's see if we can get them in the denominator. So this is called rationalizing the numerator, And the reason you're going to multiply it by the square root of 7 plus 2h plus the square root of 7 is this is the factored form of the difference of two squares. This is a minus b, a plus b, so it comes out to be a squared minus b squared, and that's how you get rid of those square roots. All right, this is called rationalizing the numerator. You spent a lot of time in your earlier days of algebra rationalizing a denominator. That was getting the radical out of the denominator. So here we are just rationalizing the numerator. Okay. All right, so let's see what we get. You get the limit as h goes to 0. All right, when you multiply the square root of 7 plus 2h times the square root of 7 plus 2h, you're going to get 7 plus 2h, right? Because it's going to be square root of 7 plus 2h squared. And then those little inside terms cancel out. And then you have minus square root of 7 times positive square root of 7, and you get 7, square root of 49, which is 7, over h times the square root of 7 plus 2h plus the square root of 7. All right? All right, let's clean this up and see what we get. 7 take away 7. All right, and in the interest of paper here, everybody agreed 7 minus 7 canceled out? All right, now we have a 2h over a h times here. You see anything else that'll cancel out? The h's, right? We got 2h over h times. So this, everybody okay? Do I need to write it down? Okay, this h cancels out here. Now let's rewrite where we are. We have the limit as h goes to 0. In the numerator I have a 2. The denominator I have a square root of 7 plus 2h plus square root of 7. All right. We're ready to take a limit, so we plug and chug, and what do we get? In the numerator you get a 2. put a 0 in for h in the denominator, you're going to get a square root of 7 plus a square root of 7. 1 square root of 7 plus 1 square root of 7 is 2 square roots of 7, right? Put right here, this little 2h became a 0. So square root of 7 plus square root of 7 is 2 square roots of 7. And now what does that simplify to? 1 over square root of 7. And if your heart desired, you can just rationalize the denominator if you want to, or you can just quit right there. That's perfectly great. All right. The reason for this example was you have now seen 3 cases where you plug and chug and you get 0 over 0. One case was where you were able to factor, like the x squared minus 4 over the x minus 2. You were able to factor. The second case was where you came up with a compound fraction, which was like right here. You got 0 over 0, so you had to simplify a compound fraction. And the third case where you got 0 over 0 is where you had a radical in the numerator. Those are the only 3 cases you're going to see in Math 131. There are other cases of 0 over 0s, but this is all you'll see. So you've covered the types that will happen. Okay? Everybody good? Alrighty, we are ready to move into Chapter 1, Section 5. What does it mean to be continuous, a curve to be continuous at a point and differentiable at a point? Alright, we're in Chapter 1, Section 5. And the first thing we're going to talk about are curves that are continuous at a point. And we're actually going to have a theorem, or is it a definition? It's called the limit definition of continuity. And I'm going to show it to you, but first I'm going to show it to you in your book, and then I'm going to illustrate it with examples, and then we'll work from there. Okay, I'm on page 106 in your book, page 106. Oops, might have to back out just a little bit because it's right here. Okay, page 106, this is called the limit definition of continuity. And I'll break it apart as we work some examples and explain every little detail. But it says that a function is continuous at x equal to a, some point x equal to a, provided the following limit relation holds. The limit as x approaches a of the function is f of a. And you're going, what are you saying to me? So I'm going to break it apart for you step by step. Okay? And then we'll come back to it and you'll see how all this just works beautifully together. All right. Let's start with what you already know. And that's probably a visual. When you look at a graph, how do you determine where it's continuous and not continuous? How do you look at a graph of function and tell where it's continuous?
Where's it break?
All right, as long as you could trace over it with your pen or pencil, all the little points, it was continuous. But if you ever have to stop, pick up your pencil, and get back down to somewhere else, it's not continuous at that point, correct? All right. So to help illustrate this definition here, I'm going to give you some examples. Okay, visually, what you usually think of is tracing curve without picking up. I don't see a single person in here would, oh, some of you have pencils. I was going to say pen, pencil, pen. All right, you just think of it, you just trace over it and it just goes on and on and on. It's continuous everywhere. Anytime you start tracing over and you have to pick it up, then you found a point of discontinuity, All right. Here's some examples that's going to help us illustrate the example here. First thing is we're going to look at point A here, where x is equal to a. Would you say this is continuous at a? Yes. All right, let's look at the next example. I tried to draw the same graph, but I didn't do a good job, did I? Okay. All right, would you say this is continuous at A? No, not continuous. All right, now let's back up a second. I'm going to claim the y value here as B. This is B, and this is C. And this is my function. In the first example, what would you say f of A is? B, that's the y value, correct? So it is continuous at A. There's a point at A. All right? Now, this one is not continuous at A, but would you say, what would you say f of A is? C. All right. So in both of these situations, there is a y value. There is a y value when x is equal to A. But this one was continuous, and this one is not. All right, just going real close again to the limit definition. Part of it says there's a f of A in there. That means if you want to say something is continuous at A, there better be a y value there to begin with. So the point has to exist. There has to be a point. You can't just have an x without a y value. All right, that's the little part that's right here on your limit definition. All right, now, let's keep going with an example. Here's my next example. Okay. Here's my next example. All right. This is an open circle at A, and I don't have any dots around here anywhere. Would you say this is continuous at A? No. Okay, what would you say f of A is? Does not exist, correct? Does not exist. Okay, so what I was illustrating was that there is no f of A, so how can you be continuous at a point if there's not even a point to begin with? All right, so we have to have a point. So one of the requirements for continuity is you got to have an x and y value. You got to have the point there to talk about it. All right, so now let's do this. Well, let's keep that same example. What is the limit as x approaches A of this particular function? B. All right, so this one has a limit as x approaches A, but there's no point there, so it was clear that it was not continuous. All right? I'm going to the second part of the definition, by the way. All right, let's go to this one. What is the limit as x approaches A of this function? As x approached A of this function, what was the limit? B. Now, it was not continuous. It had a point. It had a limit, but the y value of the point didn't match the value of the limit, and it was not continuous. Let's go back to this example. What would be the limit here as x approaches A of the function? It'd be B, right? Equals B. You told me this one was continuous. Well, the value of the function at A matches up to the limit, and then you have continuity. All right, now we're ready to look at our limit definition, and this is illustrated right here with the definition. Okay, it says it's going to be continuous at x equal to A as long as there's a y value, there had to be a point, there has to be a limit, and those two things have to match. The limit as x approaches A has to match the value of the function there. Okay? All right, so now let's go to some exercises and have some fun. You have to have a y value, The limit has to be the same thing. All right, we're going to first look, we're on exercises on page 108. Page 108, exercises 1 to 5, and we're looking at the first examples here. All right, this is a visual. It's easy to see if a curve is continuous or not here. All right, at x equal to 0, visually, is this function continuous here? No, because it's not approaching, it doesn't have a y value. The thing's flying off to infinity. If you're trying to trace from both sides, you have to pick up your pencil. All right, at x equal -3, would you say it's continuous here? Yes. X equal to +3? Yes. X equal to 0.001, that would be that, right? It's when you're at 0, it's not continuous. This curve continues on in here, so you can get on both sides of 0.001 and get a y value there. So it is continuous there. What about at x equal -2? No, because if you were tracing it, you get to -2, but you got to pick up here. There is a point at -2, but the limit, which means you got to come from both sides, is not the same. Limit does not exist. Okay, and at x equal to 2, same thing, it's not continuous there. All right, now we're going to jump down in some of the exercises below, and we're going to use that limit definition of continuity without the picture, and see if we can get it. All right, so let's pick, which one do I want to do? All of them look fun. Let's start with number 16. Number 16. Number 16, and this is page 108, and the function is f of x equals x cubed for 0 less than or equal to x less than 1. It's equal to x for 1 less than or equal to x less than or equal to 2. Okay, and the question is it continuous at x equal to 1? And we are using the limit definition of continuity. Okay? Limit definition of continuity. All right. What's one thing has to be true to use the limit definition? We've got to have a y value. So, what is the y value when x is 1? Which one of these has exactly x equal to 1? The second one. So we're plugging it into f of x equals x, which is 1. We're plugging. This is kind of a bad problem because if you put it in either one, it was going to be 1. All right, we had to put it there because it's exactly equal to 1. Okay? All right, now what was the next thing in order for something to be continuous? You got to have a point, and then the next part was you had to have the limit. So we're going to look at the limit as x approaches 1 of my function. Well, this function breaks right around 1. So we have to look at the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. Okay, left means just a little bit less than 1. So which of these expressions, x cubed or x, is a little bit less than 1? X cubed. Okay, and when you do just like you always did, plug and chug, you put a 1 in for x cubed and you get 1. All right, this says use just a hair bigger than 1. Which one of these is just a little bit bigger than 1? X. And when you put that in, 1 for x, you get 1. Now, what do we say about the limit as x approaches 1? If the limit from the left is 1, the limit from the right is 1, the limit as x approaches 1 is 1. Okay, because we came in from the left and right, and the limit went to the same place. All right. I like to do these in steps. So the third part of the limit definition is that this y value matches the limit. So yes, continuous since f of 1 equals the limit as x approaches 1 of your function. This part right here rounds out your definition. The limit as x approaches 1 of the function is the same as the y value. Okay? Yes?
I got lost. Where does the 1, like why did you pick 1 in the first step?
Oh, because the question says determine if it is continuous at x equal to 1. Yeah, it was wanting to know at that particular point x equal to 1, is it continuous there? Okay? Thanks for asking. Somebody else probably wondered that too. Go ahead. Yes, I will. The question is, will I work another? Yes, I will. Okay? And let's pick one that looks hard. 15? 15's not hard enough. I need something else. Okay, let's do 20. Let me just make sure 20. Okay, let's do number 20. Okay, this is number 20. F of x equals x minus 1 for 0 less than or equal to x less than 1. 1 whenever x is exactly equal to 1. And 2x minus 2 whenever x is greater than 0. And the instructions ask us, is it continuous at x equal to 1? Okay, that's why we're picking 1. Oops, that's a 1 there. 0 to 1 for the first. Okay. All right. So what's the first thing you're going to check to see if it's continuous at x equal to 1? Everybody say it. Is there a y value? Right. So we're going to look when x is exactly equal to 1. Which of these am I going to use when x is exactly equal to 1? That one. So 1. That came from right here. All right. So we know we have a y value. If there wasn't a y value, then we're done. Because if you don't have a y value, you certainly don't have a point. You can't be continuous at that point if there's not a point there. All right, the next thing we want to do is look at the limit as x approaches 1 of our function. All right, so that means we have to look on both sides of 1. All right, which of these functions, and we're doing that because, see, we're right around 1 in this way it's defined. Which one of these is just a little bit less than 1? The first one. Okay, and we'll put 1 in for x. We're just doing our little plug and chug. 1 minus 1 is 0. All right, and which one of these is going to represent a little bit bigger than 1? 2x minus 2. Okay, and we'll put a 1 in for that, and we get 0. So what is the limit as x approaches 1 of my function? 0. Suppose these two numbers had been different here. What would you say? Limit does not exist, so therefore it can't be continuous if the limit doesn't exist. All right, so this one has a point. It has a limit. Is it going to be continuous? No, it's no. Not continuous since the y value at 1 is not equal to the limit as x approaches 1 of your function. Okay? That's not too bad, is it? Yes?
As x approached close to 1, or 1 minus whatever, if that had been 1, both of those had been 1, then it would have been continuous?
Yes, if both of these limit as x approach 1 from the left and right had been 1, then the y value would have equaled the limit. Yes, it would have been continuous. Okay? All right, let's look at that definition one more time, and now doesn't it look a lot easier? We're back on page 106. Limit definition of continuity means don't sketch the curve and say, I do or do not pick up my pencil. All right, that's a visual. A function is continuous at a particular value of x equal a, provided the following limit relation holds. And I always do this backwards because if you don't have a y value, why are you going to knock yourself out doing a limit? So I always find the y value first to make sure there's a point. Then I find the limit, and if those two match, we're happy, it's continuous. If they don't match, we quickly say does not exist. I mean, it's not continuous, not continuous. My brain was working for the next problem. Sorry. Okay, everybody good? Yes?
What happens if, when you get it on either side, like one matches and one doesn't?
Okay. If this one had been 0 and this one had been 3.
Not that it had been 1 to match the f of 1.
Okay, this one been 1 and this one been 0. Okay. If this one, everybody realizes this is a pretend. Don't be sleeping on me. This is a pretend. Pretend when you did the limit from the left was 0, did the limit from the right was 1. What would you say the limit is? Does not exist. In order for the limit to exist, you got to come in from the left and right going to the same number. So this limit does not exist if that's the situation. If the limit doesn't exist, it can't match the 1, so therefore it would not be continuous. Okay? Good thinking. All right, anybody else? Yes?
What if both the y value and the limit does not exist?
Oh, well, as soon as you look for the point, if there's not a y value, then you don't even need to go any further. You just say it's not continuous because I got to have a point. Now, if you had a point, but the limit did not exist, then it's not continuous. They both have to exist and they both have to match. Okay? Thank you. Good thinking. Good skills, everybody. All right, everybody good? You know what continuity means. All right, now let's go to differentiability. Oops. That's a long word. It just means does the derivative. Differentiability. It means does the derivative exist? And we're really looking at a point. Does the derivative exist at a point? All right. Now remind me what your brain goes to when you start thinking derivative. Slope of the curve, slope of the tangent line. And a tangent line is the line that best fits the curve right around that little point, right? Okay. So I'm going to do some visual examples first. And then we'll generalize and then we'll work a problem. All right. Here's my first example. And here's A. All right. Would you say that the derivative at A exists or does not exist? Remember what a derivative is. Slope of a tangent line. A tangent line that best fits the curve at that point. Why are you saying no? I hear some people saying no.
There's nothing on the other side of it. Okay. It's just...
Can I draw one unique tangent line that describes this graph right around A? You got to go to the little neighborhood around A. Well, if you're coming from this curve, okay, you remember a tangent line is like you're driving a car and you get in a curve and then you don't turn your steering wheel and you go off on a tangent, right? So we'll just drive cars. You're driving a car here and you get to this point and you just go straight, wouldn't the tangent line go flying off like this? But you got to come around the curve the other way and be on that same tangent line. So you come this way and this tangent line would be right here. So is there one line that best fits this curve at A? No. So if you can't have a tangent line there that describes it from both sides, then you can't draw a tangent line, and a derivative is a slope of a tangent line. So this does not exist because no tangent line. You can't draw a tangent line there, a unique tangent line. No unique tangent line from both sides. All right. Now, what else do you also notice about this curve that we just talked about? It's not continuous. So I just want you to note it's not continuous at A, and it's also not differentiable at A. Not differentiable. All right, we're going to summarize something in a minute. Okay, let's try another example. All right, the curve is going to look like this. All right, I want to know, I want you to tell your neighbor, hash it out. Would you say that this is differentiable at A? Based on what we just did. Tell your neighbors if y'all are agreeing. You either say yes or no.
No.
Okay, how many yeses do I have? Raise your hand. 1, 2, 3, 4, 5, 6. So the rest of your no's. All right, somebody who said no, tell me why you're thinking no.
Because the line levels off at A.
All right, so did you like try to drive a car and come up with a tangent line?
No, not really. I just saw the line go off. I knew it wasn't a slope then.
All right. You have to have a unique tangent line whether you come in from the left or from the right. Remember, that's what limits is all about. Coming in from the left and right in that little neighborhood, you got to have a unique tangent line. If you're coming this direction, where's your tangent line going to go? Straight up. So, not exactly straight, but if you're coming in this way, where's your tangent line going? Do I have a unique tangent line? No. It's not differentiable. No unique tangent line. So therefore it's not differentiable. But was it continuous here? Yeah. But yes, continuous. All right. Remember, derivative is slope of the curve. Slope of the curve. So if you're on this side of the curve, that's a very positive slope. If you're on this side of this curve, it's a zero slope. So the slope on the left is not the same as the slope on the right. But it had to be continuous in order to get a unique tangent line in. Okay, here's the next example, and then I think we'll be about ready to summarize. Oh, no, we got one more example after that, if I don't forget it. Would you say this one is differentiable at A? Yeah. If you come in around A, if you're on a curve, come in this way. I can't draw it really well. There's your tangent line. If you come the other way, it's a nice smooth polynomial. You know, you can take the derivatives of polynomials. You do have a derivative. So it's differentiable at x equal to A. It's also continuous at x equal to A. Okay, here's my last example, and then we'll summarize. That's this same curve almost. Well, not exactly the same. The question is it differentiable at x equal to A? So you got to go find that point. Now, is there a new unique tangent line up here at this point coming around? No. I got to be different. I have a unique tangent line going through the point. All right, and I'm way up here. I'm left out here in outer space all by myself. So it's not differentiable at x equal to A. All right, and it's not continuous either. Not continuous. All right, so let's round out. Yes?
Does it have to be continuous to be differentiable?
Yes! Great conclusion. That was exactly what I was trying to head to. Good for you. All right, that's one reason we taught continuity before differentiability. So here's what you want to get in your brain. Function must be continuous at x equal to A. Must be continuous at that point in order to be possibly differentiable at A. So if you have to determine if something is differentiable at a point A, you need to first make sure it's continuous there. All right? Remember, just because it's continuous doesn't mean differentiable, but you got to be continuous there to have a unique tangent line around it. This one was continuous at A, but you couldn't get a unique tangent line because the slopes were different on each side. But this one was not continuous, so you couldn't talk about a unique tangent line. This one was not continuous, so you couldn't talk about a unique tangent line. This one is continuous, and it does have a limit. Well, it is continuous because you have a point and a limit that's going to match. So when you have to talk about something being differentiable, before you get there, make sure it's continuous, and then if it's continuous, we're ready to go for the derivative to check the slope on both sides. All right, so we're going to go back to the book, and then we'll go down to the two examples after we do the picture and see if it's differentiable. All right. So we're at page 108 again, page 108, and we're going to first look to see if at these various numbers, is it differentiable? These are problems really 7 through 12. Is it differentiable? All right, so we're going to go to 0. You told me a while ago it was not continuous at 0. Do I need to make any effort about differentiability? No, it's definitely not differentiable if it's not continuous. So it's not differentiable at 0. Okay, the next one is -3. It's continuous at -3, but when you try to draw a unique tangent line, you can see the slopes on both sides are very different. One's a very positive slope. The one on the right side of -3 is a negative slope. Do you see it? So it is continuous at -3, but not differentiable. Sometimes we call those sharp points. Anytime you have sharp points or corners, you know the slope of the curve's different there. All right, x equals, where are we? 3, positive 3, right here. Yep, what is the derivative at 3, by the way? That's the easy one. 0, because you got a horizontal line in there. Okay, at point 0, 0, 1, which is on this little curve that continues to go up, yes, it's continuous there, and it's also differentiable there, because you're on a nice smooth curve, no sharp points or anything. Okay, x equals -2. Is it differentiable here? Because not continuous. X equal to 2. Is it differentiable? No, because not continuous. Excellent. All right, we're going back to problem number 16. The question says, is it differentiable at x equal 1? All right. So the first thing we had to do in number 16 before we could determine if it was differentiable at x equal 1 was to make sure it was continuous. Check, it's continuous. Once you know it is continuous, we're going to come over here and take the derivative. You got to be continuous first before you do this. Don't try to skip steps. All right, what is the derivative of x cubed for x being between 0 and 1? 3x squared for 0 less than or equal to x less than 1. Okay, what is the derivative of x? 1? When 1 is less than or equal to x less than 1. All right, so now we've taken the derivative. We want to know that we have the same slope of the curve coming in all around 1. Okay? If you're a little bit less than 1, what is the slope of the curve going to be? A little bit less than 1, what's the slope of the curve going to be?
The second part, isn't it 1 less than equal to x less than?
Whoops. Sorry. I was so excited to get to the problem I forgot to copy it correct. Thank you for straightening me out here. There you go. All right, now we've taken the derivative in general, so you have to think just a little bit less than 1. What's that slope going to be? 3x squared, so just put a 1 in there. That, don't you, as soon as you're getting a 1 in that slope, pretty close to 3. All right, if you're a little bit bigger than 1, what's the slope? 1. So this is backwards for you. This way you got a slope of 3. This way you got a slope of 1. Got a unique tangent line coming in there. Is the slope from the left and right the same? No. So what are we going to say? Not differentiable at x equal to 1. That's because the slope on the left of 1 is not going to be equal to the slope of the right of 1. Yes. If it's continuous, in order for it to be differentiable at the point, the derivative from the left and the right have to be the same. Let's get a visual on this graph and you'll see. Y equals x cubed. We know that looks like this. That's y equals x cubed. Y equals x is a straight line. So let's see if we can put our 2 up here. Okay, and this is y equals x. So y equals x cubed looks like this part from 0 to 1. Y equals x looks like this. So if you traced over it, it is continuous there. But if you try to come in with that unique tangent line, you're coming this way. That would be a tangent line with slope 3 that we just found right here. And if you're coming in this way, this is a tangent line with slope 1. You do not have a unique tangent line coming in here. Is that clear? All right, let's go to problem number 20. Excuse me?
On number 16, the things in the bracket on the side, that's just to help us with the graphing.
Oh, her question was about the restricted domain right here. It's just saying we're only defining this function between 0 and up to 1, and then from 1 to 2. And yes, that does help you with your graphing, but you have restricted domains here. Instead of all real numbers where you just graph it forever and ever, just go between 0 and 2. All right, let's look at problem number 20. Excuse me?
Continuous, so you can't.
Oh, this is where you hope you have this on a test, because life is going to be great. So the question number 20 is it differentiable at x equal 1? And everybody says no. Why? Not continuous. It's not continuous. If you sketch the graph of this, your graph at 1 is going to have a jump there. Actually, what it's going to do is at x equal 1, the y value is going to be 0. It's going to look like the value is 0, but all of a sudden you got a dot up there. All right, let's see if we can find one that is continuous and differentiable. Well, I don't think they gave you one that's continuous and differentiable. Sorry, I can't, and I'm not thinking of one right off. All right, let's flip some pages and look at the exercises and make sure we're good to be ready for tomorrow. We're just going to kind of clean up. Okay, I'm turning to the end of section 1.3. Let's make sure we're good at everything. We'll do some reviewing tomorrow because tomorrow's the last lecture before your test. Okay, I'm on page 89. Looks like you're just using the power rule for derivatives. I think we already talked through this anyway. Computing derivatives. It looks like writing equations of tangent lines to curves. And on page 90, you had some of your more interesting notation. More interesting notation for derivatives. Okay, on page 91, they were giving you a little heads up to practice with simplifying the difference quotient. Remember, this book likes to give you just a little bit before you actually get there in the next section. Okay, then in section 1.4, you had limits. I'm on page 101. You had lots of limits to practice with on page 101. Page 102, this is where we were working today. Problems 37 through 48, you're using the limit definition of the derivative. Those are the words on the test normally. Use the limit definition of the derivative. 37 through 48, be sure you practice those. We also looked at 29 to 36. You could use your limit definition to find the derivative at x and then put in the value. But if you're using your limit definition, you can go ahead and put your value in to begin with. On problems number 61 through 66, you have your drill as x goes to infinity. We had some of that drill at the beginning of class today. Drill right here. The next section, 1.5, we started talking about differentiability and continuity. And they had some little pictures on page 103 to point out that there is no unique tangent line when you got a sharp point, so you know it's not going to be differentiable at A. Here you got another little sharp point. It's not differentiable at A. Same thing with C and D. The last example is where you have a vertical tangent line. And, you know, a vertical line has a no slope and a derivative at slope of a tangent line, so you couldn't be differentiable anywhere you have a vertical line. Okay, as long as you keep up with what you're talking about there. We did the limit definition of continuity, and we just now worked a whole bunch of exercises in section 1.5, so we're good there. 1.6 we actually did in the last lecture. Those were your rules for derivatives. Some more rules, constant times a function. But the biggie in that section was the general power rule. That was last lecture. We brought the R down, rewrote how? Exactly. Decreased by 1, and you're not going to forget derivative of the inside. Got to be good, good, good. I would guess you probably have 20 or 30 points devoted to general power rule. You're going to be using it the rest of the, or derivatives, just finding derivatives. Okay, so you got all kinds of derivative problems, all kinds of general power rules. Don't forget to be looking at the equations of lines and slopes of lines. You got some word problems, bottom page 116. And then at the beginning of class today, we looked at some of our notation. This is, I forgot to tell you, this is page 120. 120. Different notations for the derivatives. Second derivative. Okay, and here's the little symbol for evaluate. Like S is a function of t, ds dt evaluated at t equal -2 means find the derivative and then plug and chug. Okay? And you have all kinds of problems in section 1.7 with different letters and different evaluations. How you feeling? Good? Answer to that's yes. Yes. Okay, have a great day, everybody.